Hello and welcome to this presentation on solving simultaneous equations. In this presentation we'll be looking at solving equations such as 5x minus 2y is equal to 5 and 6y minus 2x is equal to 11. In other words, there are two unknowns, x and y, in these equations. This presentation does assume you've seen a previous presentation related to simple equations where we undertake the basic algebraic manipulation that would be required in some of the questions here. Here's a brief overview of the simultaneous equations presentation with approximate timings stated in these square brackets. The first part of the presentation relates to an introduction to the theory and the application of the elimination and substitution methods. The latter part of the question relates to a tutorial worksheet and various questions worked through in detail from the sheet. Simultaneous equations. Sometimes equations contain more than one unknown quantity. In our previous presentation on simple equations, we had equations with just one unknown, x or t, whatever the variable was, but one unknown in the equation. But we can get equations where we have two unknowns, say x and y, and so we need two equations to be generated to solve for the x and the y values. Typical equations would be 5x equals to 8y plus 3 and x plus 3y is equal to 19. This is a pair of simultaneous equations. To solve such equations, it's necessary to determine the values of the x and the y that satisfies both equations at the same time, and otherwise we're going to solve them simultaneously. Applications of simultaneous equations in mechanical engineering that can relate to the static equilibrium of structures such as found in roof trusses, thick-walled cylinders such as gun barrels or dies, in friction belt drives shown here, or in friction clutches, in the balancing of rotating masses such as that found on a shaft and rotor, an electric motor, also within shrink fits, which again occurs on rotors and shafts. In electrical circuit theory, simultaneous equations are found by the application of Kirchhoff's laws, node analysis and mesh analysis to these kind of circuits shown over here. We will only be solving two simultaneous equations within this work, but within some analyses in industry there could be 100,000 simultaneous equations that have to be solved using computer techniques. The applications outlined above will tend to be avoided within this presentation as they sometimes cause complication to the problems being solved. So within this presentation the questions will have a more generic context when we generate and solve the simultaneous equations. Solving simultaneous equations. Firstly, equations must be generated, noting that in general terms n unknowns require n separate and distinct equations to find the solution. I've had a situation in industry where I was generating 4 equations for a particular wing structure and I couldn't solve these equations, and eventually realised that 2 of the equations were actually the same, they were just written in a different format. So you must have 4 distinct equations to solve for 4 unknowns. These equations are normally generated by applying electrical or mechanical principles into the problem. Simultaneous equations can be solved using algebraic processes or graphical methods. In this presentation we're just looking at the algebraic manipulation of equations, but graphical methods can be used where you plot the equations to the line and see where their intercepts cross. This produces the x and y values. The experience often helps in deciding the best method to solve a particular problem. There are several algebraic methods of solution available to us, and again experience can help decide which is the best algebraic method to solve a particular problem. In this presentation we're going to look at 2 algebraic methods, the first called elimination and the second is called substitution. I will concentrate primarily on the elimination method, but I will introduce the substitution method also. Here is some terminology we need to be aware of in the solutions we're going to review. Coefficients. The number that's in front of the x or y term in the equation is called the coefficient. So for example, the number 3 is the coefficient of 3x. In other words, the 3 is multiplying the x here. The number 14.5 is the coefficient of 14.5x. The number 5 is the coefficient of 5y. 5 multiplied by y. And it's also important to note that the number 1 is the coefficient associated with the x term shown here. In other words, there is a 1 in front of the x we do not write. And finally, the number -1 is the coefficient associated with negative y. Again, that's really -1y. So -1 is the coefficient. We need to be aware of that term in the work we're going to review on the following slides. We're now going to review the first algebraic method in the presentation. It's called elimination, or equating coefficients in some textbooks. With this method, one or both of the equations are multiplied to produce a pair of equations where the coefficients of one of the unknowns, the x or the y, are numerically equal. This slide is showing you an important point to be aware of related to the coefficients that we find in the equations. For example, if the coefficients have the same sign, we will need to subtract the equations to perform the elimination process. In the illustration below, we've got two equations, 4x minus 3y is equal to 11, and x minus 3y is equal to 5. Two simultaneous equations with the two unknowns being x and y. Notice the coefficients associated with the y terms are both -3 in this case. Because the coefficients have the same sign, we will subtract these equations to eliminate the y. So 4x subtract 1x, shown here, would give us 3x. And then -3y subtract -3y will actually be -3y plus 3y, and that's where we get the plus 0y in this case. Then 11 subtract 5 and gives us a value of 6. And as you can see, we've now eliminated the y unknown from the equation. We can solve for the x by simply rearranging. In other words, we've got a simple equation to solve. If the coefficients of the unknown variables have opposite sign, then we add the equations together. In the illustration below, we have a -12x in the first equation and a +12x in the second equation. This is actually a +12 here. So when we have opposite signs to the coefficients for the x terms, we will simply add the equations together. So adding the equations, -12x added to 12x will be 0x, and 4y added to 2y would be 6y. On the right hand side, 11 added to 7 is 18. And again, we can solve for the value of y because we've eliminated x from the equation. So just recapping here now, the first illustration we had -3 as the coefficient for both of the y terms. So we chose to subtract then the two equations because -3y take away the -3y is actually 0. Don't forget, -3y take away a -3y, that's actually -3y plus 3y. So -3y plus 3y is equal to 0. In the second illustration, the coefficients for the first x variable was -12 and the coefficient for the second was +12. So in this case, we simply add the equations to eliminate the x values. So that would be -12x added to the +12x, and that's how we got the 0. Example 1 here is going to use the elimination process to solve two simultaneous equations. We have two equations. 5x equals to 8y plus 3 is our first equation, and x plus 3y equals to 19 is the second equation. I'm going to outline the various steps involved in this particular case to solve for the unknowns x and y. I've just rewritten the equations here for convenience. This is from the question itself. One of the first things we may need to do is to ensure the equations are of the same format. In other words, all the x and the y terms are on one side of the equation and all the constants are on the other. So in this particular case, we're going to have to rearrange equation 1 to bring it into that format. But equation 2 is already into that format. In equation 1, we have an x on one side and a y on the other. But in equation 2, we have an x and a y on the same side. And that's what we're looking for. So slight rearrangement required here for equation 1. All I'm going to do is subtract the 8y from both sides of the equation. So I end up with 5x minus 8y is equal to 3. And I've called that equation 1 just to give it a label. So what I'm basically doing there is getting the x and y terms onto the left hand side of the equation. The second equation given in the question is in the right format. But if I want to use the elimination process, I need to get the coefficients associated with either the x or the y terms to be the same. Now in this particular question, the coefficient associated with the x term for equation 1, as I've labelled it, is 5. And the coefficient associated with the x term in the other equation is 1. We don't write the ones, but it's there. So the coefficients for the x are 5 and 1, and we can see the coefficients for the y terms are negative 8 in the first equation and positive 3 in the other equation. So what I'm going to do is to make the coefficients of either the x or the y the same. And the easiest thing I can see here is to multiply this equation here by 5. If I multiply that by 5, I will make the coefficient of the x term 5, and that's the same as in the equation on the left hand side. So all I do now is multiply throughout the equation shown here by 5. So I end up with 5x plus 15y, 5 times 3 is the 15, is equal to 95. 5 times 19 is 95. I've called that equation 2, just give it a label. So now I have a situation where the coefficient of the x terms are now the same. They're both positive 5. Example 1 continued here. I've just repeated equation 1 and equation 2 from the previous slide for convenience. Now in step 2 in this case, we're going to eliminate one of the unknown variables and we're going to solve for the other. We notice from the above equations that the coefficients of the x term are now the same and they have the same sign. So we'll be subtracting the equations shown below. So to undertake the elimination process, we'll have equation 1 and we'll subtract from that equation 2. So this is equation 1 from above, this is equation 2 from above. And subtracting the equations, 5x take away 5x would be 0, and then negative 8y take away the 15y shown here, negative 8y subtract the 15y will give us negative 23y. On the right hand side we've got 3 subtract the 95, so that's negative 92. So using the elimination process, we actually form a simple equation in this case where we have one unknown, the y, which we can directly solve for by rearranging. So dividing both sides by negative 23, y is equal to negative 92 divided by negative 23. And that gives a value of 4 in this case. So we now solve for one of the unknowns. We know that y is equal to 4. Example 1 continued. Our third step in this case is to back substitute the value of y into any of the original equations. It doesn't matter which one, whichever we think is most convenient here. I'm going to use the x plus 3y is equal to 19 equation. So all I'm going to do now is put the value of y, which is 4 shown above, into that equation and then solve. So x plus 12 is equal to 19, and then rearranging, x is equal to 7 in this case. So our final answers will be x is equal to 7 and y is equal to 4. And you can always check those by putting those numbers back into the original equations and see if the left hand side equals to the right hand side. So that's the first illustration of using elimination. What I'm going to do now is show you the second method of solving simultaneous equations, known as substitution, where we substitute one equation into the other. So we're going to take the same example, but now we're going to solve it in a slightly different way. Some of you may prefer not to review this additional solution at this stage and go straight to the questions, which will be on the following slides, and undertake those using the elimination process. If you want to see how the substitution method works, I will work through this example here. So in example 2, we're asked to solve again 5x equals to 8y plus 3, and the x plus 3y is equal to 19. Again, I've just extracted the original equations from the question. And what we do in step 1 of this process is to obtain from one equation an expression either in terms of x or y. So in other words, I'm going to take the second equation, in this case, the x plus 3y is equal to 19. And I'm going to rearrange it to make x the subject of the equation. So from above, I simply need to subtract 3y from both sides of the equation to get x is equal to the 19 minus 3y. And I've called that equation 2 here. So equation 1 is as given in the original question. I'm not rearranging that one. In equation 2, I've rearranged in terms of x. So slightly different approach here. We're not trying to get the coefficients to be the same. We're trying to arrange one equation in terms of an x or y variable. And what we're going to do in the next step is substitute that into the other equation. Example 2 continue, just repeating the equation 1 and equation 2 from the previous slide. Now in step 2 here, what we're going to do is substitute equation 2 above into equation 1 above. So equation 1 above is 5 multiplied by x, but x has been shown to be 19 minus 3y from equation 2. We still subtract the 8y on the left hand side, and that is still equal to 3. So we've substituted equation 2 into equation 1 here. And the rest of the solution is purely algebraic rearrangement to find y. So all we do now is expand the brackets, so 5 multiplied by 19 and 5 multiplied by the negative 3y. On the next line that gives us 95 minus 15y minus the 8y from above, and that's still equal to 3. Bringing our like terms together, we have a negative 15y and a negative 8y. So that gives us the negative 23y shown here. So on the next line we get 95 minus 23y is equal to 3. What I've done on the next line is subtract 95 from both sides of the equation, so negative 23 is equal to negative 92. And finally, to find the y, I simply divide both sides by the negative 23. So y in this case is equal to 4, as we found from example 1 solution. Example 2 continue, just repeated the value of y from the previous slide, y was equal to 4. So step 3 is again the back substitution process. We're going to put the value of y, which is 4 shown above, into any of the original equations given in the question. I decided to use the x plus 3y is equal to 19 equation. So putting the value of y into that, it will be x plus 3 multiplied by the 4, which is the y value, and that's still equal to 19 on the right hand side. Again, we just got to rearrange the equations before, so x is equal to 19 subtract 12, taking 12 from both sides of the equation, so we can clearly see that x is equal to 7 in this case. So we have x is equal to 7 as one solution, and then y is equal to 4 for the second solution. So we've solved the same problem, but this time using the substitution method. In example 3, we're going to solve two simultaneous equations, but using the elimination process. And these equations involve fractions. We actually have the x and the y variables in the denominator in the bottom line here. So I'm going to show you how to solve this. Again, some of you might want to skip this section and review it at a later time. You may want to progress on with the questions now. But I'm going to show you how to deal with the fraction format in this particular instance. So given two equations, this time we've got 5 divided by x plus 8 divided by y is equal to 9. I've called that equation 1 here. And we've got 7 divided by x. subtract 6 divided by y is equal to 4, and I've called that equation 2 here. We're using elimination, so we need to get the coefficients of either the x or y terms to be the same. Notice with these particular equations that they're in the actual correct format. We've got the x and the y terms on the left hand side and all the constants on the right hand side. So we do not need to rearrange the equations, they're in the right format. But I do need to factor up the coefficients of either the x or the y to make them the same if I'm going to use the elimination process. So step 1 in this particular case is straight to the factoring up the coefficients. And I've decided to multiply equation 1 by 7 and equation 2 by 5. This way I'll make the coefficients of the x terms both 35 here, and I'll be able to eliminate x from the equations. So again, be careful, we're multiplying throughout by 7, so equation 1 now multiplied by 7, that will be 5 times 7 is 35 upon x. Added to that, the 8 times 7 would be 56 upon the y in this case is equal to, don't forget to multiply the right hand side by 7, so 9 times 7 is 63. I've called that equation 1a just to give it a reference. The second equation, again I'm multiplying throughout, but this time by 5, so 7 multiplied by 5 is now 35 upon the x. I'm subtracting from that, 6 multiplied by 5 is 30 divided by the y, and that's equal to, on the right hand side, 4 multiplied by 5 is 20, and that's equation 2a as labelled. In step 2 here, we're going to subtract the two equations. We're going to take 2a from 1a, labelled above here. We're subtracting because the coefficients of the x terms are both 35, so don't forget that's a positive 35 and a positive 35 here. So because the coefficients of the x terms in this case are both positive 35, we will subtract the equations because of that. Okay. So subtracting the equations, 35 divided by x, subtract 35 divided by x is 0. Positive 56 divided by y, subtract a negative 30 divided by y, actually be a positive 56 divided by y, add a 30 divided by y. A double negative there gives you a positive. On the right hand side of the equation we've got 63, subtract 20 from that. Again for reference, just be careful of the double negative. We've got 56 divided by y, and we're subtracting from that the negative 30 divided by y. So this is a double negative that makes a positive. So that's how we end up with the 56 divided by y added to the 30 divided by y. Example 3 continued. I just repeated this top line from the previous slide for convenience. We're now going to collect the terms together. So on the left hand side, 56 divided by y added to 30 divided by y is 86 divided by y, and on the right hand side 63 subtract 20 is 43. We're back to a simple equation with one unknown here. What I'm going to do now is multiply both sides by y and divide both sides by the 43 to give me y is equal to 86 divided by 43. Just for completeness, I'll show you that transposition here. We have 86 and it's divided by y, and that's equal to 43. So I basically multiply both sides by y, so I get 86 is equal to 43y, but I don't want 43y, I just want y, so I'm going to divide both sides by the 43. So 86 divided by 43 is now equal to y. And of course y is equal to 2. But that's just for reference. That's the y is equal to 2 here. And step 3 is again to back substitute the value of y, shown above, into one of the original equations. In this case I'm going to use equation 1 from the previous slide. So that was 5 divided by x plus 8 divided by y. We now know y is 2 in this case, and that's equal to 9. So So on the next line, that's 5 divided by x plus 4 is equal to 9. On the next line, I'm simply subtracting 4 from both sides of the equation, so I end up with 5 divided by x is equal to 5. Now I have to rearrange the equation for x. Now again, I'll just show the arrangement here for clarity. We have 5 divided by x is equal to 5. 9 take away 4 is 5. So I will multiply both sides by x, so 5 is equal to 5x, and then divide both sides by 5, so therefore x is equal to the 5 divided by 5, and that gives us of course the value of 1. So our final solution for x was x is equal to 1, and from above y is equal to 2. So that's a simultaneous equation in fraction form that we've solved using the elimination process. But again, you could use the substitution process in a similar way as shown in example 2. Tutorial questions. This is worksheet 1 shown here. We're asked to solve the following simultaneous equations. There are 12 questions here. I would encourage you to use elimination initially. Some of the later questions, if you want to try substitution, that's fine. For those of you that think you can solve these questions without further assistance, then I would encourage you to stop the presentation now and attempt these questions. The answers to the questions are shown on the following slide. If you want further assistance, then in later slides I will work through some of these questions showing you how to solve the simultaneous equations. Here are the answers for worksheet 1 related to questions 1 through to 12. I'm now going to work through some of the simultaneous equation questions shown on worksheet 1, and I'm going to use the elimination process here. This is question 1. In question 1 we're given two equations, 3x minus 2y is equal to 7, and of course that is 1x plus 2y is equal to 5. So simultaneous equation, two unknowns, x and y. I need two equations to solve for two unknowns, and that's what I'm given. They're in the correct format for me. I've got my x and y terms on the left hand side and all my constants on the right hand side. Now in this particular question we can see that the coefficient of the y term in the first equation is negative 2, and in the second equation is positive 2. So they've both got the same magnitudes, which is what we always look for, but the signs are different. So in this case I do not need to factor any of the equations. I'm just going to add them together and I'll automatically eliminate the y variable. So I'm adding the equations here. So 3x plus 1x is 4x, and negative 2y added to positive 2y, that will be 0. I don't need to put that in, but I'll write it in for convenience. On the right hand side, the 7 add the 5 is equal to 12. So my equation is simply 4x is equal to 12, and all I do is divide both sides by 4 in this case. I'm back to my simple equation, so it's 12 divided by 4, and that gives me a value of 3 for x. I will need to back substitute the value of x into an equation. It doesn't matter which equation I use. If I was to call this equation 1, just to give it a reference, and this equation 2, I'm going to back substitute x into 2, because it looks the simplest equation to use in this case. So from x plus 2y is equal to 5, I know now that x is equal to 3 from the previous calculation, and I'll add to that 2y is equal to 5. Rearranging the equation, I'm going to subtract 3 from both sides, so 2y is equal to 2, and then dividing both sides by 2, I get a y is equal to 1. So in this case, my x is equal to 3 and my y is equal to 1. And we can always check that by putting the value of x and y into the original equation. Put the value of 3 into the first equation. 3 times 3 is 9 for the x, and we take away 2 times the y, that's 2 times 1, so 9 take away 2 is 7, so that one checks out. And if I use the second equation, I've got 1 times x, that's 1 times 3 is 3, added to 2 times the 1, that would be 5, and of course we can see that's also correct. So So we can always check by putting the values back into the original equations and seeing if the left hand side equals to the right hand side. In question 2 we're given two equations, but notice the coefficients of either the x or the y are not the same. In the first equation shown we've got 2x plus 3y is equal to 5, and in the second equation we've got 1x plus 1y is equal to 2. So the coefficients are all different. So I'm going to show you a slightly different format here to undertake the process. I'm going to write the equations again. This is 2x plus 3y equal to 5, it's reading the question, and 1x plus 1y is equal to 2. I'm going to give them labels here. I'm going to call this equation 1, just to give it some kind of handle, and I'm going to call this equation 2, again, just to give it some kind of handle. The easiest thing I can see to do here is to multiply equation 2 by 2, and then I will make the coefficients of the x terms the same. So I'm just going to keep equation 1 as it is, so I'm basically going to multiply that by 1. But equation 2 I'm going to multiply by 2 because it will make the coefficient of the x term 2, and then I'll be able to eliminate x from the equation. So just following this through, I'm going to keep a nice structured format here, multiplying the first equation throughout by 1. Of course I get exactly the same equation, 2x plus my 3y is equal to 5, and multiplying the equation 2 throughout by 2, I will get 2x plus 2y is equal to 4. Notice we've multiplied throughout by the 2 there. Because the coefficients of the x terms are both the same, 2 and both positive here, I will subtract the equations. Okay, because the coefficients have the same sign for x, I subtract them to eliminate them. So 2x subtract 2x will be 0x, that's gone. 3y subtract 2y, that will be 1y, and then 5 subtract 4 on the right hand side will be 1. So y is directly equal to 1 here. Just take a moment to understand how we've arrived at y is equal to 1. Now I'm going to back substitute y into, and I can choose any equation I like. I think I'm going to use equation 2, that's the simplest one to use. So therefore x plus 1 is equal to 2. That's the 1 in here for the y term. So therefore x is equal to 1. Subtract 1 from both sides, we get x equal to 1. Question 3, we're given 5x minus 2y is equal to 5 and 6y minus 2x is equal to 11. We need to be careful here because although the x and y terms are on the left hand side of the equation, they're not structured in quite the same way. There's nothing wrong with the way they're structured. In fact, mathematically they're correct as written, but it's not quite the format we want. So just be careful here. So I'm just going to write the equations again of 5x minus 2y is equal to 5. And I'm just going to rearrange the other equation. I get negative 2x plus 6y is equal to 11. Just written them slightly different. Don't forget it's a positive 6y there. Same approach as last time now. I'm going to label this as equation 1 and label this one as equation 2. And I think in this case what I'm going to do is multiply equation 1 by 3 because that will make the y coefficients then the same. They have different sign but the same magnitude, and I'll be able to in this case then add the equations to eliminate y. So I'm going to multiply equation 1 by 3 to make the negative 6y as a coefficient, and I'm going to leave equation 2 as is. I'm going to multiply it by 1 effectively. You could, if you wanted to, multiply equation 1 by 2 and equation 2 by 5, and that would then make the coefficient of the x term, the magnitude of the coefficient would be 10 then, but I'm just going to factor one equation in this particular case. So factoring equation 1 by 3, I will get 15x minus 6y is equal to 15 on the right hand side there. And then equation 2 I'm leaving the same, just factor it by 1 effectively. So minus 2x plus my 6y and that's equal to 11. As the coefficients of the y term are different senses, we will add up the equations to eliminate y. So in this case, adding the equations together will remove y from the equation and will solve directly for x. So 15x add a negative 2x, that's 15 subtract 2, so that's 13x, and then the negative 6y add the positive 6y will be 0, and then 15 add the 11 is 26. So rearranging here, just divide both sides by 13, so x is equal to 26 divided by 13. So x is equal to 2 in this particular case. We're now going to back substitute the value of x into, and I can choose which equation I want to. I'm going to use equation 1 here. So 5 multiplied by the x, which is 2, minus 2y is equal to 5, so that's 10 minus 2y is equal to 5. I'm going to subtract 10 from both sides of the equation, so negative 2y is equal to negative 5, and I'll divide both sides of the equation now by negative 2, so y is equal to negative 5 divided by the negative 2, so I get 2.5. And here's an alternative solution to question 3 using different factors. In other words, in this solution, equation 1 is now being factored by 2, and equation 2 is now being factored by 5. So that now means we can eliminate the x terms from the equation. Notice we are still adding the equations as we have a positive 10x and a negative 10x. So eliminating x from the equation, we solve directly for y, and y is 2.5 as in our previous solution. And then back substituting the value of y into equation 1, we can solve for x. And x is 2 as before. The only difference between the solutions is that in the first solution we essentially only factored one equation in this case to eliminate y and solve for x, whereas in the second solution we factored both equations to eliminate x and solve for y. In question 4 we're given two simultaneous equations. This time the variable has changed. Instead of having x in y, we now have p in q, but it doesn't make any difference to our solution process. Notice that the coefficients for the p in the first equation is written as 2, but in the second it's 3, so they're different. And for q in the first equation is written as negative 5, in the second the coefficient is positive 10. So all the coefficients are different. So we need to factor an equation here if we're going to use the elimination process, and I think what I'll do is factor equation 1, that's written there, by 2, and I'll eliminate q from the equation. So that's my thinking process here. So just rewriting the equations for convenience, I'll call this equation 1, this equation 2, just give them labels, and I'm going to in this case multiply equation 1 by 2, and equation 2 I will leave the same. So multiplying the first equation by 2, that will be 4p minus 10q, and that's equal to 4. So multiplying throughout by 2, and the second equation here I'm leaving as given. So notice the signs for the q coefficients are different, so we will add the equations to eliminate q. So 4p add 3p is 7p, and the negative 10q add the positive 10q, that will obviously be 0. And adding 4 to 8.6, we will get 12.6. So therefore 7p is equal to 12.6. So p is equal to 1.8. So now back substituting p into, choose any equation I want. I think I'll choose equation 1. 2 multiplied by p, which is 1.8, minus 5 multiplied by q, the unknown, is equal to 2. That would put in the 1.8 into the equation 1. So 3.6 minus 5q is equal to 2. Subtracting 3.6 from both sides, so negative 5q is equal to negative 1.6. So q is equal to negative 1.6 divided by negative 5, and that equals to 0.32. So again, we solved our simultaneous equation. Here's an alternative solution to question 4. In this solution, different factors are used. So here, equation 1 is being factored by 3, and equation 2 is being factored by 2. This process now allows us to eliminate p from the equations, as the coefficients of both terms are now 6. Notice in this solution we have to now subtract the two equations to eliminate p from our solution. We now solve directly for q, and q is 0.32 as in our previous solution, and then back substitute the value of q into equation 1. We solve for p, and p is 1.8 again as in our previous solution. So that's just an alternative way of solving question 4, but in this solution we had to factor both equations to eliminate p, whereas in the previous solution we effectively only factored one equation to eliminate q. Question 10, this time we have decimals, but again that doesn't bother us, just different format of the equation. I call this equation 1, equation 2. I think what I would do here is multiply equation 1 by 2, because I'll get the coefficients of the y term to be the same. So I'm going to multiply this by 2 and keep this one the same. Multiplying by 2, I'll get 0.2 x plus 0.4 y is equal to negative 0.4, multiplying throughout by the 2. And equation 2 I will leave the same. Again, as the coefficients for the y term have different signs, I will add the equations to eliminate y from the solution. So add in 0.2x, add 1.5x is 1.7x, and then the 0.4y, add the negative 0.4y, obviously 0, and then add in the negative 0.4 to the 10.6 will give me 10.2. So rearranging for x, x is equal to 10.2 divided by 1.7, so x is equal to 6. Back substituting x into, choose any equation we like here, I'll go equation 1. So 0.1 multiplied by 6, x is 6, add to 0.2y is equal to negative 0.2. Then put the value of 6 into the equation. So we get 0.6, add to 0.2y, and that's equal to negative 0.2. Subtracting 0.6 from both sides of the equation leaves us with 0.2y is equal to negative 0.8, and therefore y is equal to negative 0.8 divided by 0.2. That gives us a value of negative 4. In question 11 we're given two simultaneous equations, but in fraction form this time. I'm just going to rewrite the equation in a slightly different format. So x upon 2 added to y upon 3 is equal to 3, and then 7x divided by 8 added to y divided by 2 is equal to 2. Just like a different format there. Multiplying by a half is like dividing by 2. So half of x is the same as x divided by 2, and a third of y is the same as y divided by 3. Just like a different format. I think it's easier to see what's going on in this particular format. I'm going to call this equation 1 to give it a reference here, and this equation 2 again for reference. What I would do here is multiply equation 1 by a half and multiply equation 2 by a third. That way I'll make the coefficient of the y terms 1 upon 6. So multiplying throughout by the 1 upon 2, I will get x upon 4 plus y upon 6, and that's equal to 3 upon 2. If it helps you think of the 3 being over the 1 here. For equation 2, multiplying throughout by the 1 upon 3, I will get 7x divided by 24, and that's 3 times 8 is 24, plus my y divided by 6, and that's equal to 2 divided by 3. Again, think of the 2 being over a 1 here. Because the coefficients of the y term are both 1 upon 6 in this case, I will subtract the equations to eliminate y. So subtracting, I will get x upon 4, take away my 7x upon 24, my y upon 6, subtract my y upon 6 is 0, and that's equal to, on the right hand side, 3 upon 2, and I'm subtracting from that 2 upon 3. I'm going to use fractions here to help me solve this. So I'm going to find a common denominator on the left hand side, which will be 24 here. So 24 is the common denominator for 4 and 24. 4 goes into 24 6 times, so I'll get 6x, and I'll take away from that 7x. So the common denominator of 24 on the left hand side. On the right hand side I use a common denominator of 6, because 2 and 3 divide completely into 6. 2 goes into 6 3 times, so 3 times 3 is 9, and 3 goes into 6 twice, so 2 times 2 is 4, so it's 9 take away 4 on the top. Simplifying on the next line, 6x subtract the 7x is negative 1x, so negative x upon the 24, and that's equal to, on the right hand side, my 5 divided by 6. Multiplying both sides by 24, I get negative x is equal to 5 multiplied by 24 divided by 6. So therefore negative x is equal to 20, or x is equal to negative 20. I'm now going to back substitute x into, choose whichever equation I want to here. I think I'll use equation 1. So negative 20 divided by 2 plus my y divided by 3 is equal to 3. The negative 20 has gone into the x value here. If I now look for a common denominator on the left hand side here, that will be 6. So 6 is common denominator. 2 divides into 6 3 times, so that will become 3 times negative 20 is negative 60. And I add to that 3 divides into 6 twice, that will be plus 2y on the top, and that's equal to 3. If I multiply both sides by 6, I will now get negative 60 plus 2y is equal to 18. If I add 60 to both sides, 2y will equal to 78. And then dividing both sides by 2, y will equal to 78 divided by 2, which will equal to 39. And there's a solution for the question given. Here's the bibliography used to help generate the presentation. I hope it's been of interest to you. For your reference, there is a second presentation where we apply the techniques outlined here to practical problems in descriptive form. Once you feel confident at solving the simultaneous equations in this presentation, I would encourage you to review the practical problems in the second presentation.